This is John Gardner, Professor of Mechanical and Biomedical Engineering at Boise State University, and welcome to Module 5 of Industrial Energy Efficiency Process Cooling. In this module, we're going to talk about energy savings opportunities. We're kind of wrapping this up, right? We've had bits and pieces of the different technologies that show up in industrial refrigeration systems, and we've talked about how we analyze those. And so today we want to talk about the typical things we look for when we're visiting a facility and how we recommend that they save energy with that. So quickly review here, right? The refrigeration systems are almost always based on the vapor compression cycle, and they have these four components, right? The compressor, the condenser, the expansion valve, and the evaporator. And these are typically what they look like. The expansion valves, by the way, are usually hidden. They're pretty hard to see when you're walking through a facility, but compressors are pretty obvious. The condensers, as we mentioned, are on the roof, and the evaporators are in the cold space. So the first thing we can do is eliminate things that are adding heat into the cold space. That seems kind of obvious, right? But you'd be amazed at what we find. For example, freezers, refrigerators, and these cold warehouses, they need some lighting. And if you remember from any analysis of lighting, in almost all lighting systems, about 90% or 98% of the energy that goes into lighting ends up as heat. So if there's incandescents, that's a really bad place for them, though those are rare these days. But even fluorescent lights, the 40 or every 40-50 watt bulb ends up adding about 40 watts into the heat of the building, which has to be removed by the refrigeration system. So this is a great place to recommend both occupancy sensors to turn lights off when no one's there, and LEDs. In these big warehouses, you have forklifts coming and going, moving pallets of frozen French fries and things around. Forklifts give off a lot of heat. And so you might want to go to, say, electric forklifts if that's possible. Check the insulation. Make sure that there's not insulation falling off the wall. Make sure there's not places where they missed it. Make sure the doors seal well. They should all have weather stripping. You should never be able to see any light around a door. The evaporator fan motors, the fans that drive the air within the freezers across the coils to remove the heat. If they're an older system, you want to look for ways to improve the motors, and those are called ECM, electronically commutated motors. That's a common upgrade. Particularly in the food processing area, they have to periodically defrost the evaporators because the food has a lot of moisture in it, and the moisture condenses out on the coils, freezes, and then impairs the ability of the system to remove heat. And so if you see frost somewhere, you want to see, well, can we control the humidity somehow? Can we make sure we only defrost when we have to instead of on a schedule? And finally, the way you want to look and see how they cool the compressors. These big screw compressors have to be actively cooled. Sometimes they do it by re-injecting the liquid into the thing, and they're using some of the refrigeration load itself to cool the compressor. That's pretty inefficient. There's another approach called thermosiphon cooling, which is a lot more efficient. Another broad area that we can look at is reducing the fan energy. On we talked about that on the evaporators and also on the condensers, right? And there's two ways to do it: either have more efficient motors, but more likely control them somehow. Usually, in the less sophisticated systems, these fans are just always on. You just turn them on, both in the evaporator and condenser, let them run. But you don't always need them. So the evaporator fans can be cycled on and off. Same with the condenser fans, but even better is if we can put them on a variable speed or variable frequency drive, and you can save a lot of energy that way. And then look at the operating regime of your system. So, the outside temperature, here's a little kind of cartoon. Let's say the outside temperature is 70 degrees Fahrenheit, and your refrigerated space, the freezer we're working with, is -5 Fahrenheit, which is pretty typical. Well, that means that the condensing temperature, the temperature of the gas that's coming out of the compressor has to be quite a bit higher than ambient because they have to be able to drive the heat to the ambient. So maybe that's 15 degrees higher, so that's 85 degrees. And the refrigerant that's in the evaporator has to be considerably lower than the refrigerated space, because again, you have to suck the heat away. The heat has to be driven by a differential. So another 15 degrees, so that's at minus 20. That means the lift, the difference between the low temperature and the high temperature is 105 degrees Fahrenheit. And the overall efficiency of the system is really driven by the lift. The higher the lift, the less efficient it is. So anything you can do to try to drive those two things closer together really improves your efficiency. So you lower the lift by either lowering the top pressure or raising the lower one. Okay, so the discharge pressure, that's the pressure in the condenser. And that's being set usually by a combination of how the condensers are being controlled and how the compressors are being controlled. And the whole idea here is to try to get more surface area, more ability to transfer heat in the condenser, so you can do it at a lower delta T. So you can run it at a lower temperature, which means run the compressor at a lower pressure. Okay. Sometimes that means just maybe we could recommend adding another rooftop condenser if there's space for it. For a really big system, that might really be useful. Often these, if they're old condensers, the fill, the area where the water gets sprayed on them, are full of scale, right? So we need to maybe they need a better maintenance plan for it. Maybe the fans aren't running as well or as good as they can be. On the lower side and on the bottom side, ask them if they really need to be running at that full low temperature, that low suction pressure, right? So we might be able to just raise that up a little bit. So that's the bottom bullet point there. Reconsider temperature targets. That's the kind of thing that can cost very little to implement, but it save a lot of energy, because for every degree Fahrenheit we lower the saturating pressure up on the condensing side, we can save up 1% of the power. For every degree Fahrenheit we raise the suction conditions, that's 2% power. So you can really make a big difference just by changing some settings. And often they don't even know, the operators don't even know whether those were the right settings. In other words, you ask them, did you try something different? When was the last time you evaluated this? This could be a big game changer for them. And then if there's multiple compressors, you want to look into see how they're controlled. In other words, usually you don't need all of them all the time, so there's a strategy for dispatching one compressor over another. And usually you want to run compressors as close to full capacity as possible. And the one that's maybe you've got, say, of these three that you see here, maybe two are running at full capacity, the other one at partial capacity. That one that's running at partial capacity will be called the trim compressor, and that's the one you want to have fitted out with equipment that will maximize its efficiency at partial load, and that almost always means a variable frequency drive. You don't need a variable frequency drive on all three of them. If they're running full capacity, they're fine. You won't benefit from a VFD. So usually you just need one of a bank of compressors to have a variable frequency drive, and that's particularly important if you've got a system where the load can be highly variable. In other words, there'll be sometimes when you only need one compressor, sometimes you need all three. That's where you can really benefit from a variable frequency drive. Okay, so that's really quick overview, but I want you to spend some time with the readings to get a better understanding of it. So I've got 3 readings posted, and they're fairly simple. They're very brief. You should have no trouble getting through them. One's a very short article called 10 Cooler Ideas and they basically highlight 10 ways that we can 10 measures that we could use to improve energy efficiency. There's another one, a very brief one called Evaporator Condenser Control, looking at how those there's a typo, evaporative condenser, so it's controlling the rooftop units. And then an ASHRAE article on variable speed drives for evaporator fans. These all came out of a group at the University of Wisconsin-Madison called the Industrial Refrigeration Consortium. They have provided really excellent information on how these systems work. So here's the table that I pulled off the 10 Cooler Ideas one. So we'll walk through these really quickly before we wrap up. So the strategies are listed from high value to low value. So that second last column over there talks about whether, how much energy you're likely to save. There's a column called operational risk, which is how much you might mess up the operation if you get it wrong. That's something that every, particularly food processors, are very sensitive to. And then we have capital costs, right? So floating head pressure control, basically what that means is we want to change the way the compressors are controlled to let the condenser decide how much cooling you need, how high the temperature of the discharge has to be able to reject the heat. It's usually just a control system change, and it can make a big difference. And that was the whole point in that homework assignment about looking at the bins of temperatures, wet bulb temperatures for different for the condenser for a typical meteorological year. It can tell you when you can run the compressor at a lower temperature. Saves a lot of money there. This last column here, these are sections from the Industrial Refrigeration Guidebook. I have a copy of this. I don't know if there's a copy of it up in Moscow or not, but if anybody's interested in some of these references, please let me know and I'll make sure you get a hold of a copy of it. Raise the suction pressure. That's the same thing we talked about. In other words, don't make the refrigerant have to go as cold as it's going. Put variable frequency drive on the evaporator fans. That's a particularly interesting one because that has two benefits, right? It makes the it requires you to use less energy to drive the evaporator fans, but also because the evaporator fans are in the cold space, it reduces the heat that's being added to the cold space and then reduces the load of the compressor as well. Variable frequency drive for the condensers and for the compressors. Those are also always possible operations. There's a possibility for heat recovery, so we're down at strategy 6. In other words, the compressors get really hot and they have to remove the heat. And if there's a system where you've got a bunch of compressors right next to, say, the boiler room, you could use heat recovery from the compressors to preheat the water on the boiler and save some energy there. Item 7 is the one I referred to a couple slides ago. And if you have several compressors and you have varying capacity of varying need for refrigeration, how you control the compressors, how you dispatch them one after the other is very important. The last one, hot gas defrost, that's talking about how we defrost the evaporators. I'm not going to talk about it here because there is a discussion about that in this article. Let you read that. In fact, same with the other two. So that's pretty much it. There's do the reading. I'm going to have a quiz posted soon that'll be based on those readings. No problem set associated with this. So this is more informational, kind of get this set, and then in 2 weeks, in the second week in November, we will post kind of the final project to be able to wrap up the whole class, and hopefully be able to wrap it up before your finals week for your other classes. So that's it.